Alright, Assalamu alaikum. So in this video, we'll be finishing off with binomial theorem. We started off in the last video and we'll complete it in this video. I told you it's not a very long chapter. And after that, we'll be making two videos just on the past paper questions because that is where the main problem in this chapter comes in. Right. So before we kick on in the contents new in this video, let's very quickly review what we studied in the previous video. So I told you in the previous video that a binomial is an algebraic expression comprising only two terms. So that is something like maybe a plus b. And in this chapter of binomial theorem, we'll see what happens when a whole number power is applied to an entire binomial. That is, as in, what will the expansion be when such a case happens? So let's take a look at a particular expansion. Uh, I'll do the expansion of a plus b to the power of 5. We did it in the last video as well. I'll just do it again in this video for a quick recap. So a plus b to the power of 5 gives us a to the power of 5. Add 5a to the power of 4 times b. Add 10 times a to the power of 3b squared. Again add 10 to the power of a square b cubed. Add 5a b to the power of 4. Add b to the power of 5. So we can make a number of observations here. The first observation is that the total number of terms in this expansion is 6, which is one more than the power applied to the binomial. So the first observation is that number of terms is equal to 1 plus n, where n is the power of the binomial. Now, if you take a look at any term in the expansion of this binomial, you'll see that these terms consist of two parts. The first part is the coefficient. We call this coefficient the binomial coefficient. And then we have the powers applied to the components of the binomial. Powers of the components of the binomial, that is a and b of the binomial. Right, so this means that any binomial expansion is going to have two components, two parts. The first part would be arranging of the powers of the components of the binomial, and the second part would involve application of the binomial coefficient. Right. The second observation that we can make from this expansion is regarding the powers. So we can see here that the first term has the first component of the binomial with the maximum power. And in the successive terms, what happens to this component? Its power decreases by 1 at every step. So you can see that the first step has a to the power of 5. The second term has a to the power of 4. The third has a to the power of 3. And this decrease goes on until in the last term the power of a is 0 and hence it's not written at all. Conversely, what happens for the second component of the binomial? The second component of the binomial has a power of 0 in the beginning. Therefore, it's not written at all. And in the successive terms, the powers of the second component of the binomial increase by 1. So you can see that in the first term, the second component of the binomial, that is b, is non-existent. However, in the second term, b has a power of 1. In the third term, b has a power of 4, and this increase continues until in the last term, the second component has the maximum power, that is equal to n. So the second observation, I'm not writing down the second observation. The second observation pertains to the arrangement of powers. So let's take another binomial and we'll quickly do the procedure of arrangement of powers in that binomial. So I have a plus b to the power of, let's say, 8. Alright, I'll not do a plus b, I'll take something else. Let's have 2x squared add 3x to the power of 8. So the first component of the binomial has a maximum power here. It's 2x squared basically. Sorry for the error. Yeah, yeah. 2x squared, whole of it has a power of 8. Add. Now the first component undergoes a decrease in power. So 7. And the second component now starts to gain powers. So this becomes 6 now, and 3x now gets the whole squared. 2x to the power of 2 has a power of 5 now. 3x whole cubed. Add 2x squared to the power of 4 times 3x to the power of 4 again. Add 2x squared to the power of 5 times 3x to the power, to the power of 3, the power of 5. Then add 2x squared to the power of 2 times 3x to the power of 6. Add 2x squared to the power of 1 times, I'll write 1 here, 3x to the power of 7. Finally, we have the last term, that is 3x to the power of 8. Done. We are done with the arrangement of powers. Now comes the second step of binomial expansion, and that is application of the binomial coefficient. In the previous video, we studied something called the Pascal's triangle and how it's basically a triangle of binomial coefficients. And the problem with that method was that it's a really clumsy and inefficient method, and that for very high powers, using the method of binomial of obtaining by of the Pascal's triangle would be extremely long and inefficient, and therefore the mathematicians needed something much more efficient, and that efficiency was obtained using the NCR formula. So what was NCR? NCR was actually the abbreviation of n factorial upon r factorial times n take away r factorial. I won't review the factorial notation in this video. I covered it in sufficient detail in the last video, so you can go back to that video. I guess it starts from minute 34, and it's, I think, a 7 to 8 minute segment. You can go to that video and see that. Right. So in this notation, NCR, what is n? N is the power of the binomial, power of the entire binomial. And before we move on to R, there's another observation that we made in the last video, and that is that the coefficient of the first component of the binomial was always equal to 1. And therefore, we don't need to worry about that. The worry starts from the second term. And therefore, R will be given a value of 1 in the second term. So this would be 8C1, this would be 8C2, 8C3, and C is basically just telling us that function, C is basically a function, just like logarithm is a function, C is also a function. So obviously C does not have a value. 8C3, then 8C4, 8C5, 8C6, 8C7, and 8C8. Right. So we are now done with this expansion. Obviously, as we open the brackets, more simplification can be done, but we are not doing it right now. Now, from this expansion, I want you to notice something. The first thing that you can notice very obviously is that this is the first term, this is the second term, here we have the third term. R is always 1 less than the term. So R is basically term number, take away 1. This is important and we'll come to this later in the video. The second thing is that whatever R is, that is always the power of the second component of the binomial. See, we have R as 5 here, and R is the power of the second component of the binomial as well. This tells us a very important thing, that is that R will always be the power of the second component of the binomial. So what about the first term? What about the first component of the binomial? Now let's take a look here. The power is 3. What's the relationship between n and r and 3? And it's very simple. 8 take away 5 is equal to 3. Let's move on here. What's the relationship between 1, 8 and 7? That's right, 8 take away 7 is equal to 1. This means that the power of the first component of the binomial in every step of the expansion would be equal to n take away r. So, we come to two conclusions here. Number one, r is the power. Alright, I'll just write this down in a different way. I'd like that you copy this down with yourselves. In every term in the expansion of a binomial, comma, number one, r is the power of the second component of the binomial. And n take away r is the power of the first component of the binomial. Having said that, let's now deduce a very general expression for the expansion of a binomial a plus b to the power of n. I'm not giving n any value this time, and we'll obtain a very general expansion this time. So, a plus b to the power of n would be equal to, alright, we know that for the first term in the expansion, we don't need to worry about the coefficient. Why? Because it's always 1. So the first term in the expansion becomes a to the power of n. In the second term, we would have a to the power of n take away 1, because we know that there is a decrease in the power of the first component of the binomial in every successive step, and again in the power of the second component. So it's b to the power 1 here. This is followed by yet another decrease in the power of the first component and yet another increase in the power of the second component. And again the same thing here. This continues until we reach the end of the expansion, whatever the value of n is, until, let's say, the power here would be, alright, I forgot to give some space here. Yeah. So it would be something like a cubed b to the power n take away 3 add a squared b to the power n take away 2 add a b to the power n take away 1, finally b to the power of n. Now let's apply the binomial coefficients. So n is something that remains constant everywhere. N C N C. This comes here. Now let's talk about r. And we know that r is the power of the second component of the binomial. So here r would be 1. Why? Because the second component of our binomial, that is b, has a power of 1. Here it would be 2. Why? Because the second component of the binomial b has a power of 2. Here it's gonna be 3. Here it's gonna be n take away 3. Here it's gonna be n take away 2, n take away 1, and n. So this is a very general binomial expansion. Right. Now we'll take a look at this binomial expansion and we'll derive something called a general term formula. Now before we move on with the general term formula, I'll just number the terms here. This is term 1. This entire thing is term 2. This entire thing is term 3. This entire thing is term 4. This would be term n plus 1. Why? Because we know that this is the last term of the sequence and the total number of terms in any binomial expansion is n add 1. So this is obviously going to be term n plus 1 because we have n here, so n plus 1. Right. So now the first thing that you should observe is the relationship between the term number and r. This tells us very clearly that for any term, r is actually 1 less than the term number. Let's turn the mirror to the other side. It means that term number is actually equal to r plus 1. So any term in a binomial expansion can be said to be term number r plus 1. That is, the value of r in the expression, you add 1 to that and you will get the term number. Right. So what is term r plus 1? You can see that it's n c r a to the power of n take away r and b to the power of r. Let's discuss this once again. So we are talking about term number r plus 1. So term number r plus 1 means that in this term we would have NCR. Why? Because this was a third term and this was a fourth term, sorry, and therefore we have R as 3 here. So this is term number R plus 1. So we'll have NCR here. And we know that R is the power of the second component of the binomial. So B gets the power of R. What about the first component? It's N take away R. So this formula that we have just derived here, we have just from observation, this is called the general term formula for a binomial expansion. So why is this formula particularly useful? The use of this formula is that you can use this to directly find any term in a binomial expansion. I'll give you an example. Let's say that you have a question that says that find the fifth term in the expansion of maybe 2x square add 8 to the power of 12. So there are two ways to go about it. The first way obviously would be to start off with your expansion and stop at the fifth term. A shorter and a smarter method would be to use the general term formula directly. So the general term, according to the general term formula, because we need to find the fifth term, so r would be 4. So we are actually finding the t 4 plus 1, and that would be 12c4 times 2x squared would be given a power of n minus r, that is 12 take away 4, and 8 would be given a power of 4. So this is how the general term formula can be used very directly to find a particular term in any expansion for any binomial. Right. So far so good. Now let's talk about another case. It's a simpler case this time. What if I simplify my binomial a plus b to the power of n a bit? By that I mean that this time instead of a, Let's have 1. So maybe I have a binomial like 1 plus b to the power of n. The general expansion of this would be 1 to the power of n. I'll keep this here as well so you can take a look at this here. So 1 to the power of n plus nc1 times 1 to the power of n take away 1 b to the power of 1 add nc2 a to the power of, sorry, a is 1 actually, no? So this is 1 to the power of n take away 2 times b to the power of 2, so on until we reach somewhere like n take away 2 upon times 1 to the power of 2 and b to the power n minus 2 add n take away 1 to the power of 1 times b to the power n take away 1 add n b to the power of n. Now this thing can be made simpler. Why? Because we know that whatever power we apply to 1, we'll always get 1 and we don't need to write 1 in multiplication cases. So in such an expansion, we can very simply remove these terms. And the expansion therefore for 1 plus b to the power of n would become 1 add nc1b add nc2b squared add n take away 2 b n take away 2 n take away 1 and finally n b to the power of n. So things become a bit simpler when we have 1 as the first component of our binomial. Why? Because once again the power of no matter what power you give to 1, it always remains 1. So we don't need to worry about the powers of 1 in the expansion of a binomial which has 1 as its first component. Instead, the thing to worry about is the second component of the binomial, and it's just the second component of the binomial that will be written. So based on that, for such an expansion, the general term formula obviously would become simpler as well. So TR plus 1 would be NCR because A is 1 and whatever the power you give to 1, it stays 1. So we don't need to worry about this. So it would be B to the power of R. Simple. Uh, but again, this applies only when the first component of the binomial is 1. Component is 1, nowhere else. So it's always, if you want to remember just one of those formulae, remember this one, right? Because this applies to all cases, but this applies only when the first component of the binomial is 1. So far so good. Now let's come to the last thing in this chapter. The last conceptual thing in this chapter. We'll still be left with past papers and they're pretty tricky. So far, in the last video and in this video, all binomials that we have considered have had plus signs in between the two components of the binomial. But what if there is a negative sign in between? Something like a minus b to the power of n. So for that, let's go back to O-level maths and let's take a look at the expansion of a take away b whole squared. And that gives us a squared take away 2ab and b squared. You can observe one thing here very simply, that there's an alternation of positive and negative signs. The first term is positive, the second term is negative, followed by a third positive term. So this is T1, T2, T3. So there are two observations that we can make here. The first one, positive and negative signs, positive and negative terms alternate. Which, starting with the first positive term. So the first term would be positive with a positive term. Another interesting thing, this negative term would always be the even term, right? So the second observation is, if the term number is even, if the term number is even, then the coefficient, then that term would be negative. Why? Because we can see here that the odd terms are positive. So let's make a general expansion for a plus b to the power of n, a minus b to the power of n, and this would be a to the power of n. The second term would be negative nc1 a to the power of n take away 1 b. The third term would be positive nc2 a to the power of n take away 2 b squared. Now we are on the fourth term, no? And we know that even terms are negative, so we have a negative sign here, minus nc3 a to the power of n take away 3 b to the power of 3, and so on and so forth, because we don't know what n is. So I won't write the ending terms, because depending on whether n is an odd number or an even number, obviously the ending terms would show some difference. So we can get a very fair idea of how an expansion would proceed if there is a negative sign between the components of the binomial. With that, we are done with all the conceptual stuff of the chapter of binomial theorem. A very quick review. In this video, we first reviewed about the arrangement of powers of a binomial expansion. Then we did an example here. Then we studied, then we made a general expansion of a plus b to the power of n, in which we observed that the first term has the first term is actually the first component of the binomial with the maximum power applied to it. This first term undergoes a successive decrease by one power in the successive steps of the expansion, and b, which is the second component of the binomial, starts gaining powers one by one. And then we observed another thing, that is that when we apply the binomial coefficient NCR, R is always the power of the second component of the binomial. Then what about the first power? The first component of the binomial. The power of the first component of the binomial is n take away r. And on the basis of that, we derived a general term formula, that is TR plus 1 is equal to NCR times a to the power n take away r times b to the power of r. And what's the logic behind r plus 1? That is that uh, r basically is always 1 less than the term number. And therefore, if we look at it from another angle, term number is actually equal to r plus 1, and that gave us our general term formula. And then I told you the use of the general term formula. The general term formula is used to find any particular term in any particular expansion for any particular expansion without going through the process of expanding to that term. And we did an example here of that as well. Then we discovered how we can simplify the expansion of a plus b to the power of n if a is equal to 1. And I told you that because whatever power we give to 1, it always remains 1, and we don't need to write 1 in multiplication cases. So if I have a binomial something like 1 plus b to the power of n, I don't need to worry about the powers of the first component of the binomial. and we have the expansion here. But again, this case applies only when the first component of a binomial is 1 and nowhere else. Finally, we ended our video on this that a plus that what happens if we have a take away b to the power of n, and I told you that in such a case there is an alternation between the positive and negative signs, with the even terms always being negative. With that, we are done with the chapter. We'll now be starting off with the past paper questions from the next video. Till then, assalamu